These are notes for LT6 in the sound and wave unit, and the target says that you can apply the use of the Doppler effect to modern technologies such as Doppler radar. Alright, so the key here is Doppler effect. There's a gizmo that goes along with this called Doppler shift. It's the same thing, okay, tomatoes, type thing. There's no difference. It's the same phenomenon. And a lot of what I talk about here, it's important because the day we do this, we also do the gizmo, that you get that taken care of. All right, so if you're doing this from home and you don't have the handout that goes with the simulation, even just firing up the simulation on Explore Learning and playing around with it, you'll see some of the things that I'm talking about. So here we go. Definition first. It's a longer one than normal, so sorry about that. Doppler effect. It is the apparent change in frequency due to the motion of the sound source or the observer. Alright, so if you're in class, I make this funny noise. Okay, we talk about little kids, and when you're little, everybody's played with a little toy truck or a little toy car or a little toy motorcycle or a little toy airplane, and that neom sound that we all learned to make. I don't think any of us were nerdy enough to know that that was the Doppler effect, but that is really what you were simulating. All right, that's the noise you made was that for a reason. What the Doppler effect is not, it has nothing to do with loudness. Of course waves lose their amplitude the farther they get from the source. Okay, they're going to lose some of the energy in the medium. That is not the Doppler effect. This is not amplitude or loudness. Okay, that has nothing to do with the Doppler effect. The Doppler effect is an apparent change in frequency. Now, as soon as you see the word apparent, that almost means that it isn't real. Okay, and I know that sounds strange, then why are we studying it? There isn't truly a change in frequency in terms of what is making the sound. So when that car goes "nyom" by you, or if you're standing on the side of the road, think about it. The noise the car is making is being produced by the engine, the tires on the road, the frequency at which the engine vibrates, the frequency at which the wheels and the road interact to create the sound. Those aren't changing rates as they come closer to you or farther away. Okay. Now our perception, that's very real. Otherwise this wouldn't be a thing. All right. So our perception of it is definitely different. But if somebody lays on a horn, you see them coming down the road and they're so darn excited to see you, they start honking a long ways away. If they just leave that horn on, you're still going to hear a change in pitch. Whatever it is in a car that makes the horn honk, okay, it's vibrating at a constant rate. It's not like a circus horn here where it's changing frequency as it goes towards you or away. All right, so we have to remember if it's frequency, it is a wavelength thing. Okay, this is what it is wavelength. That is what we have to remember because that determines frequency. Now, again, look at the gizmo. Play around with it a little bit. Set a stationary source where the speed of the source is 0. Watch the waves go outwards. Then have the source move and watch how the waves bunch up because this learning target is all application. All right, so we're going to apply it to technologies. So one of the first ones we're going to talk about is a police radar or even a sports radar. All right, so police radar, the one that a police officer would use to determine how fast you are driving. Let's pretend that we have, and my cars look like roller skates, so make this a judgment-free zone here. So here's my roller skate, and let's pretend it's me. Over here, gonna have a police officer, also in a roller skate, but they have a fancier roller skate. It has a little bubble on top. There, that's a police officer. So lens, police. We've all seen a police officer at rest oftentimes, stationary in their vehicle, and they are radaring. They're checking people's speeds. What that what they are doing is sending out radio waves. All right, so a radio wave is not a sound wave. A radio wave is an electromagnetic wave. And it sends out these radio waves at the exact same frequency. So in other words, the wavelengths should be identical of these outgoing waves. I know mine aren't perfect, but we're used to that. So the police officer would send out, or his radar gun would send out waves at a constant wavelength, a constant frequency. Okay. Now, these radio waves, if they hit an object, obviously they're going to bounce back, right? So some of them are going to go around, but some of them are going to bounce back to the police officer's car where they have the sensor. So they're going to be reflected. Now, what's going to happen if an object is traveling towards the police officer? Okay, they're traveling towards the police officer. So here we go here. This car, which I forgot, my roller skate, am coming towards the police officer. I'm going to smush those waves together. So the wavelengths that return are going to be closer together. Okay, because I'm bouncing them back to him. Okay, I'm bouncing them this way. So here we go. I know it looks messy. So it's important we write down here that we would see reflect at a shorter wavelength. Now, if I'm going the speed limit, then they're going to be close together, but they're going to register an appropriate number on his radar gun. So let's say the speed limit was 25, they're going to be closer together. And so if they come back to here at the wavelength that this thing is programmed to understand is 25 miles an hour, I'm fine. But let's say I'm going 45 and a 25. I would never do that. But let's say I'm going 45 and a 25. These waves are going to be even more closely spaced together, so that when the computer chip receives these waves back and they're at such a high frequency because the wavelengths are so short, that's when the computer program shows the police officer that I'm out of control, I'm going 45 and I should be pulled over. All right? So that's the use of the Doppler effect for radar guns. Same thing if I'm behind the backstop getting the reading on one of my pitcher's fastballs. All right? I stand behind that backstop and I bounce these radio waves off of the softball as it's coming towards me, towards the gun. Then I'm sending them out at a specific rate. They hit the ball is pushing them back at a shorter wavelength. And if my pitcher's trying to throw a fastball, she wants that wavelength to be as absolutely short as possible, because that means the ball's going faster. All right, so that's the gist of how radars work. Let's say that I was turned around, I'm going away from the police officer, so they're hidden somewhere and they're trying to catch me doing something I shouldn't be doing here, speeding. The waves are going to hit me if I'm traveling this way, the waves are still going to hit me, but when they return to the police officer, there'll be longer wavelengths. So if those waves are too widely spaced, the wavelengths are too long, radar gun sees, she's going 45 and a 25, that's too fast. Okay, maybe they're just a little bit longer because I'm going the speed limit. All right, so again, that won't make much sense unless you run the gizmo simulation so you can actually see these things in action. All right, another example, Doppler radar. So the weatherman, the weatherwoman, all right, maybe you're looking for a snow day. What happens at channel 9 and 10 or WNEM5 or maybe your weather bug satellites on your phone. Now, this is not a banana on a stick. It's going to look like one, but let's just say that that's a radar satellite on the ground, and it also works at the radio wave frequency. All right, so these are real long waves. If you listen to the radio in the morning, let's say you listen to 95.3 CFX, it's the signal that 95.3 CFX is tuned into. That's a 95.3 kilohertz frequency. Okay, so if you listen to 94.5, it's 94.5 kilohertz. So make sure you know radio waves are not sound waves. So Doppler radar is going to send these waves out again at a fixed wavelength, and if they don't return, if they don't come back here, then there was nothing for them to reflect off of in the sky, which means there's no clouds, there's no storm system. It's going to be a clear, sunshiny day. But let's say here comes a cloud. Going to bring the rain, man. So here, even got lightning. Now that's fancy right there. That kind of looks like an ice cream cone, now that I notice it. But all right, let's say when these waves hit the cloud, let's say that they're going to come back, but let's say that they return at a longer wavelength. So the waves that return back to this dish actually have longer distances between crest to crest or trough to trough. That means, yes, there is a storm up there, but that storm or that front or that cloud, whatever, must be moving away from this site. All right, so that would be when the forecaster says, all clear to go to school, we're not going to get anything. All right, but if the waves come back and they return at a shorter wavelength than they were sent out, so at a shorter wavelength, that's when they're going to tell us that we've got a storm moving towards us. Move towards us. Or towards the satellite that's sending these out. Alright, so if returning waves come out stretched out farther, the object's going away. If the waves come back with a shorter wavelength, so smushed together, then we know that the storm is coming towards us. Alright. Okay, we're almost there. This is a long one. Next unit, we're going to talk about this electromagnetic spectrum a lot. So for right now, I'm going to simplify it. Here's these radio waves again. All these waves are generated the same way. Radio waves naturally have long wavelengths. They're low in energy. They're really safe waves. On the other end, we have gamma. As we know, well, beyond the Hulk here, I know that's very necessary for that, but gamma waves, talking about nuclear bombs, perhaps, unfortunately, unhappy things like cancer treatments, radiation, uses gamma rays. These are crazy short wavelength, and obviously they then are very high energy, not as safe of waves. And then it's a spectrum, so there's all kinds of different intensities as we move through here. So long wavelengths are the radio waves. Your cell phone actually works in a frequency right between the radio and microwave, so it's a combination of both. So this would also be what you warm up leftover pizza with, all right, that frequency. We have infrared, so just think living animals are giving off what we shouldn't call heat, but we do, so infrared waves. So a little shorter wavelength, higher frequency yet. And then we have Roy G. Biv, okay, colors of the rainbow. So this is the only light that we actually can see. This is all technically light, but that's visible light. Then we have ultraviolet, so wear your sunscreen so that doesn't damage you and give you skin cancer. And then X-rays. It's the reason those technicians hide behind the wall when they get you ready for an X-ray, then they step away. Okay, you can't be exposed to these a lot. It will mutate your cells. They're too high of energy. All right. What we care about today is Roy G. Biv. So I'm going to write it like this, horizontally. Notice that red is a longer wavelength. So of all the colors that we know to exist, my favorite color is purple, purely coincidental that I'm writing in purple. My least favorite color is yellow, all right? So I could say, oh, I'm not buying any yellow clothes, but ultimately, the difference between purple and yellow is a crazy, crazy, crazy small difference in its wavelength, okay? They are so darn close to each other. So this color versus this color, the only difference is this has a slightly longer wavelength, so the different receptors are activated in our eyes to give us this color. This one has a shorter wavelength, which activates different receptors in our eyes, and we perceive it as this color. All right? There's almost no difference at all. Almost no difference, physically speaking in terms of physics. Now, we're going to be having a unit here at the end of Physical Science B. It's an astronomy unit. And in that unit, review. Most accepted scientific theory is that the Big Bang Theory did happen, right? So everything we know to exist in the universe was once together, and pressure buildup goes boom. All right, and so scientists have accepted, all right, the most accepted theory is that the universe is expanding. But the question would be, how do we know that? Right? How do we know it's expanding? We can't even get to 99.9% of the universe. So how do we know it's getting farther away? And it has to do with what is called a red shift and a blue shift. So red shift, blue shift. And I always feel like Dr. Seuss a little bit there. What is it? One fish, two fish, red fish, blue fish. Come on, you know what I'm talking about here. So red shift, blue shift. We can analyze stars, all right? It's called a spectral analysis, and we'll look at this at the end of, again, the last unit in this course. Spectral analysis of starlight is shifting. So the starlight that is traveling towards us is shifting to the red end. So in other words, over time, we have seen longer wavelengths coming from these stars. Longer wavelengths. Red is longer than the violet. That is showing us that those stars are getting farther away from each other and farther away from us. That's why we know that, scientifically at least, we can't dispute that the universe is expanding. Okay, we're seeing it get stretched out. Now, something that's crazy and is disputable is why. Because gravity pulls. You would think that, well, yeah, we went boom a long time ago, that everything within the universe would start to tug on each other and pull itself back in. What's happening is we are starting to go away from each other faster and faster. So we are starting to get farther, let's say from Alpha Centauri, another star. Like, we're getting farther away from that star at a faster and faster rate. But why would we do that? Because once it goes boom, there's no air drag, so I can understand maybe not slowing down. But why are we speeding up? It's not like there's a jetpack on stars and jetpacks on meteors and asteroids and whatever, making them go faster away from each other. And that's where this idea of antimatter, anti-gravity, dark matter, dark energy, all that. There's something else going on. Just make sure you understand the flip side of the coin. If all of a sudden, the astronomers are watching these spectral analyses come in, and they start to see, whoa, starlight is shifting to the blue end, well, that would then mean that the universe actually is starting to contract, okay? But it's not doing that right now. We're seeing longer wavelengths come back, which means that the universe is expanding. Okay, lots there. So take some time and really think about that before you take this learning target. And again, I would make sure that gizmo is taken care of, the Doppler shift gizmo, before I took this target. Good luck.